Okay, Gen Chem kids, we are going to talk about one more trend on the periodic table today. We've talked about atomic size, we've talked about ionization energy, and today we are going to talk about what is called electronegativity. We've also talked about the electron patterns. I guess that's another trend as well. Okay, so electronegativity is a lot like ionization energy, but it's kind of different. So instead of seeing how much energy it takes to remove electron, we're measuring how much that electron is attracted to the nucleus of that atom when it's bonded. So the electronegativity of an element, let's define it here. The electronegativity of an element indicates the relative ability of its atom to attract. So we're talking about the ability of the atom to attract electrons in a chemical bond. So there are two things that we need to be aware of here. We need to have a bond made. So what I mean by a bond is that element or that atom needs to be sharing an electron with another atom, or maybe even swapping an electron with another atom to create an ion. But it needs to be bound in some ways to another atom, either by sharing an electron or swapping an electron. Okay? So, and then the other thing that I want you to realize here is we are doing a relative scale. So what we are doing is we are comparing one atom and how strong it is to another atom and how strong that attraction is. So we're doing comparison between two atoms that make the bond. Okay, so we're comparing between two atoms. Electronegativity values are assigned on a relative scale. The highest electronegativity is fluorine, and the lowest value is francium at 0.7. Fluorine is 3.98. So let's look at these values on the periodic table, and let's see if we can see some kind of a trend here. So I've got a periodic table here that has the electronegativity values. And you'll notice that there is indeed a trend. So as we go down the periodic table here, our electronegativity values also decrease. But on the other side, if we go across the periodic table like this, our electronegativity values increase. So that basically tells us a couple of things. It tells us that the general trend, and I'm going to put in the general trend by way of just a highlight line through here. So the general trend of electronegativity is this way. Okay, that is the general trend. So when we look at the general trend here, these in the corner up here would be our largest or our highest value. So those are going to be our largest or our highest values for electronegativity, and these down in this corner are going to be our smallest or our lowest values. Okay, now the other thing I want to point out here, let's change color once again. Now if I look at this, my highest values are in this upper corner, and I kind of highlighted that before. Nitrogen, oxygen, and fluorine are our absolute highest values when we talk about electronegativity. In fact, when we get into bonding, they have such a high affinity for electrons or electronegativity that they are able to create a special kind of bond called the hydrogen bond. And we will talk about hydrogen bonds in a week or two, probably. Notice that the trend is not completely uniform. There's this group here in the middle that actually have pretty high electronegativities, and that's due to their high densities. They're super dense materials. That's a very advanced topic, and we're not going to get into there. I really just want you to know this general trend that is laid out by this magenta arrow here. Okay? So my next question here is, let's look at this question right here. Why do you think the noble gases don't have any assigned electronegativity values? Notice these, the noble gases, don't have any electronegative values assigned. Why do you think that is? Take a minute and think. Do you have an answer? So let's see if your answer is correct. Remember, one of the things that I said about having an electronegativity value is we are comparing relative strengths of attraction of electrons in atoms that are bonded to each other. Now, bonded means that we have to react with other elements. Do the noble gases react with other elements? No, they do not. And because they don't, that's why the noble gases don't have electronegativity values. So, the noble gases don't react. And because they don't react, they don't make bonds. And one of the things for an electronegativity value is in its electron sharing within a bond. So because we don't make bonds with the noble gases, we have no electronegativity values. Okay, so let's do some practice problems. We're going to look at some elements, and we are going to practice ordering atomic radius. We're going to practice ordering ionization energy. We're going to practice ordering electronegativity. And I'm going to throw some things in here. We haven't really talked about ions and size. Just so that you know, for this last one, ions, negative ions make larger atoms than the neutral atom, because I put more electrons in that electron cloud, and then I get electron to electron repulsion going on without extra protons to pull those electrons in. So the electron to electron repulsion kind of takes over and makes that electron cloud even bigger. And then positive ions make smaller atoms than the neutral atom. So if I have a positive ion, that means I've taken electrons away, but I still have all those protons in there. So because I have fewer electrons, the protons overpower the electrons, for lack of a better word. And I have more protons in that little nucleus pulling in on those electrons than I have electrons. So the electrons get pulled in even tighter. So the positive ions are always going to be smaller than the atoms that they come from. Okay, so let's get the periodic table out and let's highlight strontium. Let's see, we need to highlight strontium, tellurium, magnesium, sulfur, and silicon, and see if we can understand the radius. So let me get the periodic table out. Let's see, periodic table, let's get this open. Okay, so we need to highlight a few elements. Let's make this a little bit smaller so that we can highlight all of them. I'm going to move this up here so we're not blocking the periodic table, and let's get our highlighter out. if it will let me. Okay, so strontium. We need to look at strontium. We need to look at tellurium. We need to look at magnesium. We need to look at sulfur. And we need to look at silicon. Okay, now remember, the atomic radius trend goes from small up here to big. Okay, so we want to start with, it says on our practice problem to do increasing radius. So we want to start with our smallest and end with our largest. Okay, so I would say, and remember, each time we go down, we are adding a new layer or a new shell. Okay, so our smallest one here is going to be sulfur, and then we're just going to pick it up to silicon and then magnesium. Okay, so let's go back on our thing. So sulfur is going to be, so we want to start with our smallest. So our smallest is going to be sulfur. And then when we look at that, we have silicon next. That was also on the same row. And then magnesium was also on the same row. Okay, and then if we go back and look at our periodic table, we've got sulfur, silicon, and magnesium. A lot of kids will wonder why I didn't put tellurium instead of magnesium. Remember, tellurium has 2 more shells on it, 2 more layers. So it's going to be bigger than magnesium, even though it's on this side of the periodic table. And then next would be tellurium, then strontium. Strontium is going to be our largest. So we will have tellurium next, and then strontium being our largest. Okay, so arrange the following elements in order of increasing ionization energy. Okay, so we're going to have the same elements. Let's look at our periodic table. Now, we're going to talk about ionization energy. Remember when we talked about ionization energy? That trend was exactly the opposite of size. So ionization energy gets big on this end. Okay? So we're going to look at the opposite trend. So if it's the opposite trend, could I take the list that I just made with these same elements and just reverse it for ionization energy? I would say that the smallest ionization energy here would be strontium, because it's the one closest down to this lower left-hand corner. Then it would be tellurium, then magnesium, then silicon, then sulfur. So I'm going to take the list that I wrote for the atomic size and completely reverse it for the ionization energy. So my smallest ionization energy is going to be strontium because it's got the largest atomic radius, so those electrons are going to be the easiest to pull off. And then tellurium, and then magnesium, then silicon, and then sulfur. Sulfur is going to be the largest ionization energy because it has the smallest atomic radius of these guys, and therefore the electrons are going to be the closest to the nucleus and the hardest to pull off. Okay, let's look at increasing electronegativity. Now, if we look at our periodic table, isn't that trend pretty much the same as ionization energy? Now remember, it is, except one thing. Electronegativity does not have the noble gases, but we don't have any noble gases here. So because it is pretty much the same trend line as the ionization energy, we could do the same list that we did for our electronegativity and ionization energy. They should match up pretty well. So let's look at this. So I'm going to do the same list. So my smallest electronegativity is still going to be strontium because those electrons are not held very closely, and so they're not going to share electrons with a very strong pole. Then would be tellurium, then magnesium, then silicon, and then our highest electronegativity would be sulfur because those electrons are held closer. So those nucleus are going to pull those electrons in tighter when it is in a bond because of the smaller radius. So largest. Okay, now let's double check this really quickly. I'm going to double check these with the ionization energies that are posted in this chart that we have up here. And we're going to check this out. So sulfur, 2.58, silicon, 1.90. So let's write those down, 2.58 and 1.90. So 2.58 for the sulfur. Oh, I don't like how that moved. 2.58 for the sulfur and 1.90. Okay, I'm going to let you guys go and check with magnesium and tellurium and strontium and put those values in and see how well our trend line did. Okay, take a minute and do that. Okay, you ready? Okay, so strontium is at 0.95, tellurium is at 2.1, and magnesium is at 1.31. So how did we do in terms of our trend line? I think we did pretty well, all things considering. Now remember, trend lines don't get everything. Do you see that tellurium is kind of the odd man out? And it's the odd man out because it is in that fifth period where things get really dense. If we really wanted to order it, we'd put it here. But notice, except for tellurium, we are really pretty much in order. Now remember, once again, trend lines don't always get everything, but getting 4 out of the 5, it's a pretty good trend line. Okay, now let's arrange the following ions in order of decreasing atomic radius. So if I do decreasing, I want to start with my largest. Oops, let's make that a pen, not the highlighter. So I want to start with my largest. Now I'm going to do something here. I want to look at the proton to electron ratio on all of these to help me make my decision. So let's just take them in order. So fluorine being a -1, fluorine -1, fluorine has, let's look in our periodic table. Fluorine has 9 protons. So we have 9 protons, and if I have a -1, that means I have 10 electrons. Okay? Let's look at selenium here. Selenium has a charge of -2. So selenium, let's find selenium. I've got 34 protons there. So selenium, 34 protons. And if I have a charge of -2, yeah, that's not going to let me erase, is it? There we go. If I have a charge of -2, that means I have 36 electrons. I have 2 more electrons than I have protons. Let's look at beryllium. Beryllium has a +2, so that means we were missing 2 electrons. So beryllium, we have 4 protons. We have 4 protons, and if I am missing 2 electrons, that means I only have 2 electrons. 2 minus 2 is 2. Okay, and then bromine. Bromine -1 is called bromide. So let's look at bromine. 35 protons. 35 protons, and if I have a charge of -1, that means I have 36. Oh boy. 36 electrons. Okay, now remember, if I want to go in terms of decreasing radius, I want to start with my biggest. So my biggest one is going to be negative, and it's going to have the most electrons. So notice this. These two are both negative. They both have the same amount of electrons. Now the thing is, how many protons do I have pulling in on the electrons? The least amount of protons is going to be bigger because I'm going to have more electron to electron repulsion. So the largest here is going to be selenium. So selenium -2 is going to be the largest. And then bromine -1 is going to be the next largest. Okay? Now let's look at our smaller ones. Fluorine is negative, beryllium is positive. Negatives always make a bigger atom. Positives always make a smaller atom. So we would say fluorine -1 would be the next biggest, and then beryllium being positive would be the smallest because they're on the same energy level. So that is how we would order those in terms from largest to smallest. All right, so your homework today, we are going to do some more ionization energy practice, and we are going to do some comparative electronegativity practice as well. All right, have a great day. We'll talk to you later. Bye.